to Dalton's April seminar. This one is on nuclear hydrogen and hydrogen in general. Been a lot of buzzing about in the media recently, particularly a large announcement back in December about the government putting in lots of money towards nuclear and hydrogen technologies. Some of that overlaps. We've got some great speakers today. We've got some online speakers as well, who may be joining later on. Just to let everyone know that this meeting will be recorded. So if you could take your phones on silent, which I'll make sure that mine is. Yes. And if anyone's not okay with being recorded, please keep your cameras off on the Zoom chat as well. Right, and I will pass you over to Paul Hennessey from Jacobs. So Paul is the Emerging Markets and New Technologies lead at Jacobs, where he takes a leading role in the development of the Jacobs hydrogen business. He is a subject matter expert and consultant engineer for hydrogen projects, including green renewable hydrogen and nuclear derived pink hydrogen, from feasibility stage all the way to project execution and delivery. So I'll pass you over now. I'll just get that up. Apologies. Share screen, there we go. This one. Right. Yeah.
Thank you very much for the introduction. Just check that works and I drive it. Yeah. Okay. Hi, nice to meet everyone. Paul Hennessey from Jacobs, work in the technology consulting and innovation team. I focus mainly on the business case for new reactors, so SMRs and AMRs, and it's links to doing other things, so alternative to grid business case options. So here today, just to do a little bit open up with a bit of scene setting on hydrogen in general, the potential role of nuclear derived hydrogen, and then look at some of the use applications there. I'll quickly go through. I've been told I've only got 10 minutes, so I might skip over one or two of my slides. If that's working, no. It's at the back, that's why. Seen all the spoiler alert there then. Quick bit about Jacobs for those who don't know us. Jacobs is probably an amalgamation of lots of different mergers and acquisitions, all the way back from NCC and some parts of UKAA, Wood Nuclear, and now is the Jacobs Nuclear business. And through that full life cycle support, I work in the business case area, and helping reactor vendors look at what their reactor size and shape would be in order to match industrial applications, so they can develop the best product with the most use cases possible. So bit of scene setting. We're currently in what the government are talking about being an energy trilemma. So the 3 points of the triangle, we've got a need for energy security more than ever. That's at the forefront of thinking at the moment with the whole Russia-Ukraine crisis. We've got the whole net zero ambitions by 2050 and the whole sustainability argument. And with the cost of living crisis even more brought to the front, we've got this requirement that it's got to be affordable. And we haven't been very good in the UK of trying to work on all parts of the triangle at the same time. We kind of tend to pick one and major with that and pay a bit of lip service to the other 2 points. So it's a big challenge. We're around 107 gigawatts in terms of electrical capacity in the UK today. We only use around 40 to 50 at any one time, but we have about 107 gigawatts generation capacity. And when you look at the various policies and papers and the different industries which are looking at moving either to electrification or to hydrogen made via clean electricity, that could be pushed up anywhere between 150 to just over 360 gigawatts in capacity. So with that mountain to climb, you start to think, well, you can't really do it without nuclear being involved in there somewhere. And nuclear does offer a strong case. It's a non-intermittent, secure energy supply, and the intermittency is key for certain industries which are going to look to switch them off hydrocarbons like natural gas. It's a proven low-cost option for both electricity and, importantly, heat. And it's a net zero technology. And as Ted linked to in the start, it's some nice announcements around Christmas, and again a few months ago, nuclear is now part of that green taxonomy. So we can start to talk about nuclear properly as a green technology. And modular nuclear reactors, SMRs, AMRs, which is where I'm spending most of my time, that's now offering a pathway to open up different use cases for reactors. We can put them where you wouldn't normally necessarily look to find them in the UK, and we can twin them with industry. So, and that opens up these alternative to grid concepts, which is a new use case for nuclear. So energy mix right now, people are not involved in energy always get this wrong. The media hammers home about the need for renewables, and we need to get more wind farms, and things like fracking is bad and all that. But we're only talking about 20% of our energy use. So and these goes up and down by a few percent either way, depending on which paper you look at. But generally, the average 40% of our energy use is heat and then high grade industrial heat, and the other is in transportation. So I won't hover on these slides too long because we have only got a few 10 minutes. But 87% of us UK homes cook and heat on gas. And industrial processes which need that higher grade heat, they currently rely on fossil fuels. And decarbonising both those industries is a huge challenge. So the clean energy routes, well, we can try to electrify certain heating processes, so heat pumps and things like that for homes, although 16% of UK housing stock could never have heat pumps without huge big alterations which make it unfeasible. We can replace fossil fuels with cleaner derivatives, so hydrogen, or what we call liquid organic hydrogen carriers, so things made out of hydrogen like ammonia and methanol and sustainable aviation fuels, things like that. Or we can look at direct heat from a clean energy source such as nuclear, and this is particularly where the AMR in the UK, we distinguish between SMRs and AMRs. Confusingly, the rest of the world just call them SMRs, small modular reactors, but we distinguish between the two for the two different heats that they give off. This direct heat source from AMRs is opening up new conversations with industry which didn't really exist a few years ago. So current predictions on transport, electric power, although all the Elon Musk would hammers home and what he's up to and all the media hype about EVs, it's actually going to be a very limited effect on what we use in transportation, because it's dwarfed by what heavy goods, freight, passengers, shipping and aviation. The currently battery technology, the weight to power ratio doesn't allow any of those big users to go into electrification. So we're going to be using a liquid fuel, petrol or diesel, until replacements are available. And the one that's coming to the fore more than anything is hydrogen or synthetic fuels made from hydrogen. And we're showing a 50% increase in fuel, despite all of the talk on electrification of transport. By 2050, we're expecting to double the amount of liquid fuels that we use compared to now. So that kind of changes the energy mix in the UK to, well, we don't really know what, but we think electrical is going to really, really grow. You start to see the potential gap. That takes us to around 180, 170 gigawatts of power there, where we can see that the potential gap goes all the way up to just below 370 gigawatts when you start to plug in the strategies of industries which are saying, well, we're going to electrify, or we're going to use hydrogen made via clean electricity via electrolysis, and we're going to burn hydrogen, and that's how we're going to achieve net zero. So then you start to think, well, where is all this power going to come from? Because we're targeting for about 150 megawatts in current government policy, but you start to add up what everyone else wants to do, and we could be 370. And if you plug home heating into that, well, the numbers look absolutely silly. So we don't include it on this graph because it goes very, very high. So current ambition in the UK, we have this 10 gigawatt aim by 2030. And that was doubled about 6 months ago from 5 to 10 gigawatts. But most people in the industry think that's far, far too small, given the amount of people out there looking to switch over to potentially use hydrogen. In the UK, we used to use, and my next slide will go into the colours. And if anyone was from government here, they'd probably slap my hand because they want us to move away from blue, green and pink hydrogen. But I quite like it in a technical conversation to differentiate. We officially have carbon capture and storage utilise hydrogen and electrolytic based hydrogen. The scale of delivery is pretty huge because less than 1 gigawatt of production in the UK at the moment will be classified as low carbon or net zero. It's all grey hydrogen where you vent off most of the CO2. So we have a big mountain ahead. And if we just take the 4 hard to abate industries, if we just take the 4 hard to abate industries, we can already see that that's adding another 113, 114 gigawatts of clean energy requirement into the UK. And as I said, 10 gigawatts by 2030 is tiny compared to what we'll be using by 2050, where, depending on what you look, somewhere between 35 to 45% of all energy systems could be hydrogen based. So quickly breezing through 2 methods of making hydrogen at the moment: steam methane reforming of natural gas, and that's how we make the majority of hydrogen in the UK today. We don't capture that CO2, it's vented off. Or old technologies which have found a new lease of life: water electrolysis, so electrolyzers. And we can either directly use that hydrogen, or we can turn that hydrogen into something a little bit more practical for storing and carrying around for things like aviation, shipping and transport. So onto colours, which is one of my favourite slides. So lots of different colours of hydrogen, and this is linked to either the technology behind the power, which you use to make that hydrogen, or the carbon footprint. So grey hydrogen is what we have now, captures none of the CO2, energy intensive, steam methane reforming of natural gas, and we take the hydrogen and we let the CO2 go. Blue hydrogen tries to bring technologies in to capture some of that CO2. At the moment, it's anywhere between 50 to 90%. So the green lobby, kind of unhelpfully, because we see it as a lot of people call this the blue bridge. It's the bridge to get the economies of scale to bring green, the economics of net zero hydrogen into play. That will capture anywhere between 50 and 90%. Pyrolysis, fairly new kid on the block in terms of the hydrogen conversation. You'll now find them at most of the conferences and the seminars presenting their technology, claiming up to 98% capture rates on the CO2. Then we get into green technology, which is any net zero power supply now, so tidal, renewables, and nuclear if you did it from a grid connection. Where we start to get clever with the nuclear industry, which is where we get excited about, is what we call pink hydrogen, and the 3 pinks. So hot electrolysis, around 350 degrees C steam temperature onto a SOEC electrolyzer. You've done the majority of energy required to change from a liquid to a gas or water into steam is done very efficiently by the nuclear reactor. And we can feed that 350 degrees steam into a SOEC-based electrolyzer, which is solid oxide electrolyzer cell. And then that can quickly heat up that steam to the optimum temperature for that particular device, depending on the manufacturer, and you get quite low levelized cost net zero hydrogen. Hot electrolysis, where we can take it even further, the optimum range for electrolyzers we've worked with, they will give us like 610 to 630 degrees C. So if we have AMRs, which are most of them, because they're trying to get the UK competition guidelines, are going out for 700 to 750 degrees C. It means we can get steam off the nuclear island at around about 650 to 640 degrees C onto those devices. No energy is lost in trying to reheat that steam, and they can just go into hydrogen production. And then thermochemical water splitting, government policy sees this potentially starting to contribute to our ambition in the 2040s. There's a few different ways of doing it, depending on the catalyst used in the process. Anywhere between 500 degrees C to 2000 degrees C. You can look at that, and that gets rid of all of the capital expenditure required with your hydrogen production equipment. So think of 100 megawatt electrolyzer projects. You're looking at around £60 million worth of capital outlay on your electrolyzers. So if we can do it without the need for that, just using the thermochemical water splitting process, we've saved 60 million straight away for a project, and then the levelized cost of hydrogen comes down.
Thank you. If I could just ask you to wrap up very quickly. I'm
going to wrap up. So depending on how it's made is the technologies that it links with. We argue here that, yeah, lots of offshore wind and onshore wind going on. However, the capacity factor, which is the asset uptime, is pretty crap, really, for those technologies, where nuclear offers this very, very high uptime rate, which allows other technologies that require constant hydrogen production all the time. It opens the door for them to use hydrogen. this is a bit of the presentations will be sent out, won't they, Ted? So this is kind of what we've talked about on a slide, take you around. So all the different ways nuclear can interface. The non-intermittent clean technology is the most important part of that. Some NNL graphics on what a potential AMR site with synthetic fuel production and derivative production would look like. And I'll just look at the aviation sector quickly to finish. So this is, you can see the efficiencies of hydrogen production improving as the temperature goes up. So if we just do a grid connection, direct electrolysis, just for the aviation industry, which would need about 55 gigawatts of additional power in order to quench the thirst of UK aviation with a net zero substitute, we look at around 180 MSRs, and you can see they're going down in terms of how many assets out there in the field we would need. The big thing is at 650 degrees C, it looks like we can break below $1 a kilogram, which is where, according to the COP26 mission innovation, that's the point which all industries on hydrocarbons now could switch without a financial penalty, without it being thin. And to finish, it's not just hydrogen we can do with reactors. It's just one alternative use application. Reactors being put out there purely as a heat source for things like district heating or for to drive catalytic processes, drive industrial processes. This is now being talked about as well. So reactors might be going out there, not even touching a grid reaction connection, which is kind of new for the industry. So summary, strong case in supporting all areas of the trilemma. For hard to abate industries, hydrogen is going to be a major player. It's hard to achieve any of this without the role of nuclear, just from the sheer amount of net zero power we need. It's a low cost option, the lowest levelized cost hydrogen option potentially out there, and a high capacity factor of nuclear provides options. So the examples in the picture there are from Pilkinson's Glass and St Helens. They have 15,000 kilograms an hour hydrogen requirement for each of their furnaces, each of their sites, which is huge. And they only turn the furnaces off once every 15 years. So how can they move to hydrogen if it's linked to things like renewables? They can't. We've got people who never ever thought they would own a nuclear reactor starting to have those conversations at a high level. And that's some key enablers, but I think I've gone over time, so I'll finish there. The main thing is we need to talk about the alternative use of reactors more than the industry is doing, because it's been dominated by low, grid, providing grid for a bit too long. Thank you very much. Sorry if I went over there.
That's okay.
Yeah.
Thank you. Right, so that should lead nicely into our next speaker. We have Professor Juan Matthews at the Dalton Nuclear Institute. Juan began his career at the UKAEA Harwell Laboratory, researching and managing research in fast reactor and nuclear safety. He is currently a visiting professor at the Dalton Nuclear Institute at the University of Manchester here, where he teaches at postgrad level and has a particular interest in advanced nuclear technologies. I'll just get his presentation up. Juan, you okay to speak?
He's on mute.
You might be on mute.
You can hear me now, can you?
Yes, brilliant. So, yeah, I'll just tap on and control the slides for you.
Right, I've stolen the title here from an American Oak Ridge National Laboratory project, which is hydrogen at $1 a kilo, because I think that's what our target has to be eventually. But in the following table, if you can get the next slide up, you'll see that there are various things which are going to cause a problem in us reaching this. The one thing in Paul's slides, he mentioned that the solar load factor was 28%. Well, that's probably in the southern states of the United States, like Arizona. The actual load factor, capacity factor for solar PV in the UK, and this is the figure which is taken off the statistics from solar generation, is only 10%. And in fact, the current statement that they're looking to having some enormous 70 odd gigawatts of solar on solar farms in the UK is catastrophic, because it will just put the price of electricity up. Because it would mean that solar would be generating in summer when the electricity is not used. It would be generating maybe 3 or 4 times the amount of electricity that's actually being consumed. And as anyone who does the economic calculations, that just puts the price of everything else up. So I'm unashamedly, I'm actually very against solar for anything except putting it on your house, if you're lucky enough to be able to put in a battery and be able to use the electricity that comes off the solar. So if we compare the different sources of electricity, at the moment we've got a problem with nuclear. It's too expensive. You see that the levelized cost of producing nuclear electricity from the new build, well, it starts off with Hinkley Point C with a price of £93 per megawatt hour of electricity, compared to solar's the cheapest at 44, and a very uncertain price for natural gas. Offshore wind and onshore wind are both also quite reasonably priced. The main thing about solar is, because it's heavily dependent on capital cost, has to operate at a high capacity factor. If the capacity factor goes down, then the price goes up. So we really want to be operating on nuclear power stations 90% of the time. And that means ultimately, I think, for the electricity component of their usage, we need to be able to find some way of storing the electricity. And with the one advantage of nuclear over solar and offshore wind is that it doesn't produce electricity, it produces heat. But of course, that's the other thing that Paul talked about. We need a source of heat in order to be able to meet some of the other uses of energy in the country. The other thing about nuclear is the energy density is very high. If you see how much solar area or wind area would be required to produce enough electricity to enough energy to meet our usage, we would find that for onshore wind, that would be 63% of our land area. And in terms of offshore wind, that would be 12% of the zone that we can claim around our coast. The other thing is that the carbon emissions from solar are really quite high. And if we look at taking natural gas and mitigating it with carbon capture and storage, the carbon emissions are still extremely high. They're potentially an order of magnitude higher than nuclear, and those have to be offset. And if we went to a system where we continue to use gas, and using gas, the methane releases in accessing the gas, and the carbon dioxide releases from the leakages and the inefficiencies of carbon capture and storage, mean that we would have to put enormous investment and cost into offsetting those releases with negative carbon releases. Now, if we look at the costs of producing hydrogen, you'll see that currently the cost from nuclear is slightly better than solar, but around about the same as offshore wind and onshore wind. But when the gas price is low, substantially more than producing the hydrogen using steam reforming of methane. And then if we also look at the carbon emissions, we'll see that the potential for generating hydrogen with nuclear power is produces substantially less carbon emissions. So we go to the next slide, please. This representation here I stole from the Kirsty Gogan's paper. I quite like this diagram because what it shows is the effect of capacity factor or load factor on the price of generating hydrogen. Now, if we start with electricity as a standard electricity cost of £50 per megawatt hour, you can see that solar, the price of the hydrogen goes up very steeply because the capacity factor for hydrogen for solar PV is only 10% in the UK. As you get down to 0.4, maybe even higher eventually with offshore wind, you see that the price comes significantly down. Now, one of the things Paul's also mentioned was the ability to go to high temperatures and to use solid oxide catalytic cells using steam electrolysis. And you see that the price there is slightly better than you get from just using the electricity. One of the problems with solid oxide electrolysis cells at the moment is the capital cost is quite high, and we need to get that capital cost down, which will happen if we start to produce these cells in large amounts. Now, if we had free electricity, then we can see what the underlying reason for this behavior is, and this is the capital cost of the electrolytic cells. And you see that the PEM cells, the low temperature cells, are slightly cheaper because their capital cost is low. So if we go to the next slide, I'll just put some actual figures in here. So we can see now what the cost is of producing hydrogen using solar, and it's just economic. Uneconomic to use solar to produce hydrogen in the UK. If you take the electricity off the grid, you would have to pay the price of the electricity according to the time of day when it's used, and that will be all over the place. People say, well, why don't we use very low cost electricity when people don't want to use the power? And I've put at the bottom here the effect of free or curtailed electricity from an excess of renewables. Now, the amount of time you would have that excess would be quite limited. I would be very surprised if it was much above 10% of the time. Now, curtailed means that it's not being paid for. Now, that means that if it's solar power and they've got a contract for difference, somebody is paying, and that's you, the consumer, is paying because of the constrained price. So don't believe people when they tell you that solar can produce low-cost electricity, which will give you low-cost hydrogen. It's not going to happen. Now, what are we going to do about this problem with nuclear, with the high price at the moment? With RAB, with the regulated asset base, we should be able to get the cost of large-scale nuclear down to about £60 per megawatt hour. Now, that's still going to mean that the price of the gas is quite high. But with using solid oxide high temperature electrolysis cells, we should get it down to a similar price to the very best of offshore wind electricity. If we go to new technologies using higher temperatures, we should be able to get it down even further. And also I put on a notional figure for using thermochemical techniques, which Paul mentioned also, which will allow further reductions. But what will really bring us to be able to meet the target of £1 per kilogram will mean a combination of optimizing the design of high temperature gas cooled reactors, which are dedicated for production of hydrogen, and to also get the experience of introducing either these thermochemical techniques at high temperatures, or the large-scale production of electricity using steam electrolysis with solid oxide electrolytic cells. Now, I've provided a number of additional slides afterwards for those who, if you ask for those slides, you get my. If you ask for my presentation, you'll get some extra slides which will give you a bit more detail about the technology of using solid oxide high-temperature steam electrolysis. Well, thank you.
Thank you very much. Just check if Chris is in the room. Otherwise, would you be all right to speak? Yeah. No. Okay. Lovely. So I'll pass you over to Dr. Brian Connolly. Let's get your presentation over.
Oh, yeah.
Share. Yes. There we are. Yes, brilliant. Thank you. Yes, so Brian is the current UK research lead for the Material Systems for Demanding Environments theme within the Royce Institute for Advanced Materials Research and Innovation. That's the building we're in right now. Dr. Connolly is a reader within the Department of Materials at the University of Manchester and holds a Royal Academy of Engineering chair in corrosion performance of energy systems, sponsored by EDF Energy. Thank you very much.
Yeah, very good. Thanks for inviting me over to the talk today, or downstairs to talk today. So a little bit different from the first two talks. I want to tell you some activities that we're doing right now in the Royce Institute that hopefully will facilitate the UK's advance in this area. And so those of you that don't know anything about the Royce Institute, we're a national institute with a regional footprint. And we do that through 9 different universities across the UK, as well as the National Nuclear Laboratory and the UKAEA facilities for fusion down at Culham. Now, our mission within the Royce itself is to support growth of world-leading technologies and excellence that we have in the UK at the moment in material science. And we want to do that through accelerating commercial exportation, as well as looking to delivering positive economic and societal impact into the UK. All right, we have 4 pillars in which we support this activity. The first one, we provide access to the latest facilities and capability. So the beautiful facilities that we have here at Manchester within the hub building is just an example of one of 9 areas that we have across, 11 areas across the UK in which we have equipment and facilities for anyone in the UK to use. We also try to foster, one of our other pillars is fostering material science skills and development. We develop people here at the Royce. We also catalyze industrial collaborations and exploitations of material research. And we enable national materials research foresighting and also collaboration and strategy. And that's what I'm going to talk to you about today. And so one of the things that we do with the Royce, as well as having all the nice facilities that you can use, we connect the research community across the UK. All right? So we are always promoting material science, but we try to do this through external engagement, also convening meetings and facilitating things that we can use to push decisions through government. All right, so one of the things that I'm going to talk to you about today, and the main thing that I'm going to talk to you about today, is our activities called roadmaps and landscape. So our roadmaps and landscapes are focused on national challenges, national materials challenges. And since COVID, we have done 5 different road mapping type of exercises. So we did one on the materials for energy transition. We did one on materials 4.0, which is the digital material science, materials for fusion, degradations in structural materials for net zero. And the last one that we've done is, and we published it last year, is materials for end-to-end hydrogen. All right, so that goes beyond what we're talking about to do today in nuclear. And it was a stepping stone to our next activities. So we have two new landscaping opportunities. One is looking at biomaterials and basically linking the laboratory practices with clinical applications. And the second one that we're talking about today is nuclear-enabled hydrogen. Right? So I think this was covered very, very well in the previous two talks, but the amount of energy that we need through hydrogen and the hydrogen demand, whether it's in transport, high goods vehicles, aerospace, is quite considerable by 2050 in the UK. And all of this has to be achieved by us overcoming many different materials challenges. Right? So if we talk about this materials end-to-end hydrogen roadmap that we did last year, so it was a 3-month consultation. We interacted with more than 100 people across businesses and academia. We held cross-industry academic workshops to identify major research programs in hydrogen production, transport, and testing. We then, out of that roadmap, delivered a £140 million funding bid to BEIS and government. All right, so the Royce itself can be used as a focal point for UK hydrogen materials research. And so this diagram gives you a nice overview of the different programs that are going on, not only in the universities, but also the bigger knowledge transfer entities such as ATI, in the catapults, at MPL, at the health and safety executive, et cetera. One of the things we also do within the Royce is we develop blueprints, and also we've done a nice survey on test facilities within the UK to give people in the UK an understanding of what we have here in this country. And so a blueprint, so two of the blueprints that we've done in 2022 was the UK hydrogen testing map, and also the UK hydrogen production through electrolysis blueprint. All right, so those can be all found on the Royce website. We also have put together a materials database called HiMat Base. And so for the first time in this country, we're starting to put together a database for hydrogen applications and materials. And this was driven by basically Rolls-Royce, National Grid, and GKN. We also use seed funding to initiate research in key areas. And so last year, we were able to deliver equipment bids across 4 areas within the UK. At Liverpool, we looked to develop high throughput preparation and novel electric catalysis for water splitting. At Oxford, we developed with Rob Weatherall nanoparticle manufacture and operando studies under electrolysis. Here at Manchester, we looked to develop hydrogen absorption and desorption characterization techniques. These are very important to hydrogen embrittlement of many of the components that we see in the hydrogen economy. And lastly, we looked at scale up of PEM electrode deposition and testing down at Imperial College. All right. So the main thing I wanted to talk to you about today is the new effort that we're putting on this next few months over the summer. So we are developing a landscape activity for materials for nuclear-enabled hydrogen. All right, so what is a landscape activity? Well, basically, we've gotten together between the Royce and NNL, and we're going to organize a series of workshops with industry and also academic leaders to explore and understand the materials challenges facing the deployment of this nuclear-enabled hydrogen. Now, the workshop will form a basis for the landscape study that we'll publish. And hopefully that landscape study will develop into a roadmap, which we can use to influence government. All right, so what are we doing in this landscape activity? Well, we're gathering input. So we want to understand and get a consensus of what the key research challenges are for materials applications when we're talking about nuclear-enabled hydrogen. We want to publish a landscape report that details the results of these workshops. And we also want to use these workshops to enable communication and advocacy to the government. So we'll be having one of these workshops fairly soon in May, but we probably will look to have another one in later in the summer. Some of the key things that we'll talk about in this workshop, we'll take a look at different things that all different things materials wise that are going to be challenging for this nuclear enabled hydrogen application. So we're going to talk about electrolyzers. We're going to talk about specific materials challenges for some of the chemical reactions and chemical processes that are involved in hydrogen generation. Look at heat extract and the problems that we have there, specific failure mechanisms. So a lot of these things will have hydrogen embrittlement problems. A lot of components within either the electrolyzers or some of the other devices that generate the hydrogen will have these problems. We'll also talk about timescale challenges because we'd like to develop this and deploy it by the 2030s. And also past metals, there's a lot of seals in a lot of these devices, and they degrade in hydrogen gas. Right? So we'll talk about in these workshops, the focus might mainly be on high temperature reactors, but we'll also talk about light water reactors and how there are some applications that we can go into right now and apply or develop in places like Sizewell B and Hinkley C. Okay. So first landscape workshop is going to be scheduled for 18th of May. It'll be here in the Royce Hub building. And if you wish to attend, please send an email to either Hannah Bryson or Andrew Bofield. So Hannah is part of Delta, and so Delta is a green energy consulting group that is helping out on these landscapes. All right, that's about it.
Thank you very much, Brian. So just check it. Chris has joined. Brilliant. Right. So I'll pass you over to Professor Chris Hardacre. Chris Hardacre is the head of School of the Natural Sciences at the University of Manchester here. His group has strong research interests in catalysis and ionic liquids, and he is also a co-principal investigator of the UK Catalysis Hub and is an elected member of the Royal Irish Academy. He has over 490 publications and 11 patents. Welcome, Chris. Can you hear us?
You're on mute, Chris.
Mute. I'm on mute, so you can't hear me. That's okay.
Oh, lovely.
I'm less on mute now than I was. Let me just share my screen.
Yes, brilliant.
Can you see that okay?
We've got you.
So I was going to give so I don't do a lot of nuclear stuff. We have done some nuclear stuff in the past, but it's mainly been associated with nuclear fuel recycling and so on. So I'm going to talk a little bit about. Oh, I can't spell department clearly. Okay. I'm going to talk about other ways that you can produce hydrogen and where nuclear might have an impact in that. Obviously, we know why we need to do the produce hydrogen for sustainability and for clean energy and so on. CO2 is a problem, but in terms of how we're going to produce it, there are ways to produce it directly within the nuclear process, of course. But there is also using nuclear energy to develop hydrogen production routes through electricity, whether that be through direct electrolysis of water or through other means. Direct electrolysis of water gives you green hydrogen, but what I'm going to talk about predominantly is going to be blue hydrogen. And I don't know whether you've seen this slide, but we do need to try and make some inroads into this. So there's been a new government initiative to talking about sustainable aviation fuels, and by 2050 there's got to be something like 70% of aviation fuel has got to be sustainable. But one of the problems is what's on the slide at the moment, of course, which is effectively our demand for energy is increasing exponentially. We have a decrease in in terms of the fuel share of the fuel over the period of 1990 to 2030, in terms of percentages associated with fossil fuels, as you can see at the bottom here, coal is remaining the same, natural gas has gone up, but oil has come down significantly, and renewables has gone up. Nuclear has remained about the same, perhaps, for the outlook, and hydroelectric's gone up slightly. But because there's been this huge demand increase, the actual amount of oil that we're going to be using goes up over the period rather than going down. And so we need to be both more sustainable in our fossil fuel transformations, as well as the use of renewables and nuclear and so on. And part of that gives us our sustainability. And that requires, in the case of transformation of biomass, for example, it requires hydrogen, it requires catalysis, and it requires clean energy sources, whether that obviously be fusion or fission or whatever. And so I thought I'd just give a bit of an example of how hydrogen has a very large impact on the conversion of some of these renewables to both fuels and to specialty chemicals. So raw biomass contains lignin, cellulose, and hemicellulose predominantly, all of which are oxygenated hydrocarbons. Most of our fossil fuels are unoxygenated. So to actually get our biomass into a form that we can really utilize as a fuel, for example, we need to be able to deoxygenate that. The only way you deoxygenate it is you use hydrogen, and that hydrogen then can convert the raw biomass into triglycerides and fatty acids, through into glycerol and biodiesel, through to alkanes and alcohols, and into specialty chemicals. But you can see hydrogen is everywhere, and you can also convert raw biomass directly into hydrogen. Two ways of doing that, though, are I'm going to go through now. One of the ways is a reforming type process. So in the case of making hydrogen conventionally currently, what you do is you do steam reforming of methane. Now, of course, the hydrogen comes from the water reaction of methane with methane, producing CO2 and hydrogen. That is okay as long as the methane is biogas related. If it's natural gas related, then of course we're just using a fossil fuel. If we're going to generate hydrogen from bio-based sources, then we are likely to do it through a reforming process, and in particular, something like aqueous phase reforming or enzymatic transformation. And we've looked at a lot at photocatalytic reforming. Aqueous phase reforming is done at large scale, but it's a very energy-intensive process. Enzymatic photoproduction of hydrogen from things like cellulose is very good, except it's very slow. So photocatalytic reforming has been looked at. We can use the sun. We can use light sources that are generated using electricity, for example. To do that, what you do is you effectively, the only bit of this diagram you need to look at, can you see my mouse okay?
Yeah.
Yeah. The only bit of the diagram you really need to look at is the top right-hand corner here, where you've got a semiconductor, and you're shining light on your semiconductor, and you're exciting an electron from the valence band of the semiconductor to the conduction band, leaving behind a hole, a positively charged hole in the valence band, and generating an electron in the conduction band. The electron then does the reduction of species, whereas the hole does oxidation of species. And we generally use, to make hydrogen, we generally use sacrificial agent, and cellulose is a case in point as a sacrificial agent. And so this is effectively water splitting, but using, it's assisted water splitting using biomass. This is some work that's just been, that we published a while ago, looking at glucose. It's very easy to produce hydrogen from glucose at a really fairly good rate. You can scale this up. This uses an arc lamp, but you can use LEDs. And it's an efficient process using this, platinum on titania catalyst. Key thing though is that we don't really want to do glucose. Glucose is a sugar. It's used in food. We'd like to be able to do it just of raw biomass. We've done it with cellulose. You can see here, cellulose rate is slightly lower than the glucose rate, but it's still pretty good. And it's much, much higher than water splitting rate. You can see here, the water splitting rate that you've got there, albeit this catalyst isn't great for water splitting, but even still, this is a significant increase in the rate of hydrogen production over water splitting. We've looked at the way that this works in terms of solubilized species versus doing it on the raw biomass, and I won't go through into this in any detail, but I can go through it if you wish me to later. But what we've really been looking at is mechanisms. Here we have the hole in our valence band interacting with our cellulose to do that formation of glucose, which then overall process the electron, then interacts with the water and produces CO2 and hydrogen over the platinum system. Importantly, though, you can do it directly with raw biomass. So this was doing photoreforming of grass that was from my garden. We just picked the grass. You then just pumped it in the reactor and it worked fine. So if we could use the sun, we can do this remotely. We can do this at small scale. We can do this at large scale. Of course, we don't probably have enough sun in the UK to be able to do this, but we could power the LEDs or lights via electricity generated by nuclear power, for example. And this then gives you a way of doing water splitting with a reasonable rate. We can do it of trees as well as grass. You can see here some raw willow samples that we've done some photoreforming of, photocatalytic reforming. The key part about this slide is that it depends on where that willow is grown as to how much hydrogen you produce. So if you might want to have the willow growing on the side of Sellafield, for example, to produce the hydrogen to power things locally or produce transportation fuels or whatever it might be in the local area. And so you would choose the biomass specifically to grow in that area. You can do it in the gas phase as well as in the liquid phase, and this is some photoreforming of methanol. You can do it of other alcohols, and you get significant low temperature activity. The traditional ways of doing photoreforming of these types of things are to go up to something like 400 or 500 Celsius. So this does it at 100 Celsius, and it works very well. Part of the problem with reforming processes, though, is you don't just create hydrogen and CO2, you also create carbon monoxide, which if you're going to put the hydrogen into a fuel cell is a bit of a disaster. The CO then poisons the anode of the fuel cell, and then it causes the thing to stop working. So one way to clean up that hydrogen is to do the reaction between CO and water to give you clean hydrogen. I don't know from the nuclear perspective whether you get how much clean hydrogen you get, or whether you have other things like carbon monoxide being produced as well. But this is a way of cleaning up and improving your yields of hydrogen overall. We've done that thermally, as you saw from the previous graph, but we've also used non-thermal plasmas, which are generated by electricity, which could come from a nuclear reactor, for example, and this works perfectly well. You just create a discharge over your catalyst bed. As you can see, the catalyst bed sitting here, you create the discharge and you see this purple glow. And if you do that, what you actually get is you get very good conversions of carbon monoxide at very low temperatures. This is below 100 degrees Celsius. Typically, these water gas shift reactions operate at 250 to 500 Celsius. So we're doing this at low temperature, high energy efficiency, using the plasma reactor.
Brilliant. Thank you very much, Chris. If I could just ask you to quickly wrap up, we've only got a few minutes left. That's all right.
Yeah. We can also produce methanol via the reduction of CO2 as well, as you can see here, using that same process. Just a set of acknowledgements. Thanks very much for listening.
Thank you. for interrupting you there. Right, so we've just got a few minutes left. It's not a huge amount of time, but if anyone's got any questions, feel free to put your hand up, or even a question from panelist to panelist. That's always welcome.
If anyone online, put it in the
If
chat.
anyone's online, yeah, you can put it on the chat, which I've got open here. In the meantime, while anyone's thinking of that,
Can I perhaps ask a question about the purity of the hydrogen that you can produce from the nuclear system?
yes, who fancies fielding that? Paul,
Uh,
I've thrown you in it.
yeah, you've thrown me in it there. Ours would be, from the work we've done with electrolyzer manufacturers, it's depending on which electrolyzer we go with and which we use. Thinking of the P&IDs that we've looked at, there is a purification step for depending on what you want to use that hydrogen for. So if it's in transport with fuel cells, they need to be higher, kind of 99.999% stuff. So there's more dewatering of that hydrogen and purification of that hydrogen coming off there. So the thermochemical water splitting probably is more the nuclear having an effect on the actual purity of the hydrogen. But in terms of using the heat with SOIC electrolyzers or just powering the PEM proton exchange membrane electrolyzers or different technologies, there's 4 or 5 now out there. It depends on the individual devices.
Great, thank you.
Can I just say that for the high temperature steam electrolysis using solid oxide, it's pure steam that's going into the circuit, and the only contamination is water. So it's very pure.
Yeah, I guess the only thing in purity to mention is the input of the water into that. So EDF projects at the moment looking at kind of taking steam which would normally be used in the turbine, so coming through the demin process, and there's some questions of whether that is actually clean enough. Is the total organic carbon a little bit too high? Some of the older stations will be around kind of 200 ppb on that. Newer stations are more down to kind of below 300. So, but again, it depends on which manufacturer you work with. So there's others who can tolerate more contaminants in the steam because their materials are less sensitive to that.
Thank you. Yes, Ed.
I've got a question before. I really enjoyed the presentation. Really nice
thank
overview. And you mentioned that there's approximately 40% heat, 40% transport, 20% electricity in terms of use. And I may have missed this, but do you have an approximation of what the hard to abate percentage is of that 100%?
So I don't have a breakdown on what they would be. So the hard to abate on heat.
Yeah.
I think the biggest use of natural gas in the UK, 87% of us heat and cook on homes in the UK. So that's I can't remember what that is in terawatt hours.
That would be hard to abate.
Well, it's hard to abate in that electrification of homes has a whole load of challenges with it, because where we're going to get the extra electricity. If we all suddenly switch to heat pumps tomorrow, then grid would fall over because we don't have the extra capacity in our grid to do that. Plus, there's certain housing stock which can't go down the electrification of homes.
But so by hard to abate, you don't mean. Yeah, what I would think of as by hard to abate is something like shipping or aviation, where really it's practically impossible to use electricity there. Whereas, So there's some, I guess there's some nuances in all the percentages and all the.
So National Gas would stand up and say they are a hard to abate industry because switching from natural gas to hydrogen has a whole load of material challenges and new network challenges and things.
Right.
The true sense of the word, if you are right, the hard to abate industries are those who require really high temperature for industrial processing, so they can't go down electrical alternatives because their temperature is too high. Shipping and aviation, then you can't look at battery powered flight very easily. You can't do the weight to power ratio for batteries on ships would make it impractical.
So if you add those up, you might be talking a smaller percentage. It might be that 20%, but 1% would actually be hard to abate where hydrogen we would be able to use electricity. So that means that we will be talking such an absolutely enormous amounts of hydrogen in that case. So if we take, for instance, home heating out of the equation, where we could use electricity
Yeah.
instead, then that's a huge drop, isn't it, in the amount of hydrogen we require.
Yeah, so
And then we'd only be talking about those really, really hard things like shipping, like aviation, etc.
Yeah, well, the
So
shipping
amount,
and-
the amount we need is
Yeah.
significant.
Yeah, so that those would live in the transport 40% rather than the heating. Yeah. On the heating, yeah, industrial heating, the industrial requirement, probably about 30% of that problem. But the majority is gas for homes.
Sure.
So yeah, so in terms of what's an easier problem to solve, that hard to abate petrochemical, because there's only about 15 to 16 big petrochemical refineries around the UK.
Yeah.
So we could target those with, and solve a big slice of that problem if electrification of homes was easy to do.
Thanks.
Great. We've run over a little bit, but I'm just going to cheekily give one question to an online person. So we've got questions from Juan. How could we feasibly push electricity generation from a source with a relatively high levelized cost of production?
Yeah, well, that's perfectly true. It's a key issue for nuclear. Nuclear has got to get a lot cheaper. Now, there are several problems here. One is the investment costs for nuclear are very high, and for instance, the discount rates that you used are something like 7% in the UK. With the regulated asset base, that means that government is basically underwriting the investment. It means that we can get lower interest rates. So that means we can get the cost of nuclear down by about 30%. Now, that's still not enough. We want to get it even lower. And there are a number of ways. One way is that by building smaller power stations, we can build them more quickly. So at the moment, a large nuclear power station like Hinkley Point C takes about 10 years to build. If we build a Rolls-Royce SMR or a 300 megawatt electricity high temperature gas cooled reactor, we can build that maybe as quickly as 3 years. And that reduces the investment cost again. And then additionally, by going to modular construction, with the smaller reactors, so that most of the construction is done off-site, and also having long runs of production of smaller reactors, we should get the cost down again. So potentially we're looking to become cheaper than offshore wind.
Great, thank you very much, Juan. Unfortunately, we're going to have to end it there. But thank you very much for everyone for coming. I don't know if either of you probably have to shoot off.
I've got 15-20 minutes before I need to
Right,
get back.
well, we'll end the video here. If anyone wants to hang around and have a chat, that's absolutely fine. Yeah, and just thank you very much for coming. Thank you very much for our speakers. Thank you very much, Juan. Thank you very much, Chris.